All right, we've reached the last lesson for this semester, and we're looking at special cases of eigenvalues. So we've talked about two real distinct roots. We've talked about complex eigenvalues. Now we're going to talk about what to do if we have a repeated root or a zero as one of our eigenvalues. So let's start with repeated roots. If we have a repeated root, the general solution then is going to look like this. E to the lambda t, I just need the one lambda because it's repeated, times some initial condition plus te to the lambda t times the eigenvector that goes with that lambda value. And just make a note that x1 or x naught and y naught is going to be some sort of initial value that you'll be given. So let's look at a quick example here. Solve this system, and I'm going to find the eigenvalues same way I always do. We're going to use the determinant of this matrix. So we have -2 minus lambda times -2 minus lambda and then minus 0. And that needs to equal 0, of course. So when we solve this, my only lambda value is -2. So that's a repeated eigenvalue. I'm going to go ahead and find my eigenvector by looking at the straight line solutions again. So we know that we're going to have -2, 0, 1, -2 times xy has to equal -2xy. And so we could say -2x plus y is going to be equal to -2x, which leads us to y equals 0 as a straight line solution. So the corresponding vector, eigenvector that goes with that, we know y is always going to be 0, so let's just choose 1 for the x value. So then my general solution using this information up here is going to be in the format y of t is equal to e to the -2t times some initial condition. They did not give that to us, so I'm just going to leave it x naught, y naught for now, plus te to the -2t times the eigenvector. And that's going to be our general solution. Now, let's go ahead and take a look at what the phase portrait would look like for this. The same rules as what we had when we just talked about regular distinct real solutions, that if lambda is negative, which it was in this case, it was -2, remember that that means we're going to have a sink. All of the solutions are going to go towards the origin. So the question becomes, what direction do they take, or what path do they take to get towards the origin? Well, first of all, before I get too involved, let me go ahead and graph the straight line solution. Remember, it was just y equals 0. So that's our x-axis. And like I said, we know that they're going to go towards the origin because of the negative lambda value. But then here's my question. I could either take a path, well, let's do it this way. Before I say anything, let's do this. Let's do a couple of test, I'm going to call them test vectors. And so what I mean by that is I'm going to choose some points on the graph, and I'm going to draw the vectors at those points and kind of see what direction things go in. So let's say I just choose the point 1, 1. That's in the first quadrant. So let's say 1 and 1. I'm looking at that point right there. The vectors then would be what? So if you put in 1 into the original system of equations, the original system of differential equations, you'd get a dx dt value of -1, and likewise you would get a dy dt value of -2. So what that means is at that location, I would go -1 in the x direction and -2 in the y direction. So that vector would look like this. So here's the idea, is that that's moving in sort of a clockwise direction. Let's just try another test vector just for fun. Let's say we choose, gosh, I'm looking at my points on my graph here. I don't know. Let's just choose like 1, 2. I don't know. Let's just see what happens. So that would give me a vector of -1, and then we would have -4 for the y value. So 1, 2, that would be starting here. I would go down 1 and left 4 would put me over here. So that would be in this direction. So same idea. So the idea is everything's kind of moving in that direction. So it's moving in a clockwise direction. So my solution curves are going to go this way towards the origin, and then the same thing's going to happen down here in this quadrant. My solution curves are going to go this way, and everything is going to kind of follow that sort of pattern towards the origin. Let's take a quick look at this using technology and see what that looks like. It's going to give you definitely a nicer picture, but let's make sure we see it. So here's the same system. Notice my only eigenvalue is -2. And same thing, you can see that these are moving in sort of a clockwise direction. I don't know if I can draw on this, but they're all moving towards the origin in the clockwise direction. And so if we would test out values, even if they're still going towards the origin, we might get a sink where they're moving in the opposite direction, where they're going in a counterclockwise direction. So we'll see some examples like that as well. But notice that we have a sink, and like I said, because of that negative eigenvalue, everything's moving towards the origin. All right, last special case here, and that's what do we do if we end up with an eigenvalue of 0? So take a look at this example. Let's go ahead and start by actually calculating those eigenvalues. So just like normal, we're going to go ahead and set up our equation, -3 minus lambda times -1 minus lambda, and then -3, and we want that equal to 0. So if we solve that, we end up getting, let's see, lambda squared. I'm just going to simplify it here. Lambda squared plus 4 lambda. And then the 3's are going to end up zeroing out, so we're down to lambda times lambda plus 4. So my two eigenvalues are going to be 0 and -4. All right, so just like always, we're going to go ahead and get our straight line solutions. So we end up getting, let me start with lambda 1 equals 0. We end up getting, let's see, I'm going to write this out. I still feel like it's helpful if we write it. So we have -3, 1, 3, -1 times xy has to equal 0xy. So if I just use the top row, I have -3x plus y equals 0, and that means that y is going to be equal to 3x. So my eigenvector that goes with that, if we used 1 for x, that would give us a y value of 3. Now let's do the same thing for the second lambda. So my value was -4. So I'm going to have, same thing, I'm going to have -3, 1, 3, -1 times the xy equals -4 times xy. So we get -3x plus y equals -4x. You could also use the y component, wouldn't make a difference. But either way, I'm going to wind up getting, let's see, y equals -x, I believe, is my solution. So the eigenvector that goes with that, if we choose 1 for x, we're going to get -1 for y. So let's put all this together, and we're going to have our general solution. It's really going to follow the same format as what we had when we first started doing these, where we had two distinct real solutions. So I'm going to have k1 e to the 0t times the vector 1, 3 plus k2 times e to the -4t times the vector 1, -1. And of course 0t, that's just going to give us a value of 1. So I'm going to go ahead and write these in component form. We're going to have x of t then is equal to k1 plus, let's see, k2 times e to the -4t. And then my y component would just be 3k1 plus, or minus rather, let's fix that, minus k2 e to the -4t. Now, if it had just asked for the general solution, I would have just left it in that original version, but they gave us an initial condition, so I'm going to go ahead and use that to solve for my k values. And I'm going to skip some of the details here, but basically, when t is 0, the x component is going to be 1, so we're going to have 1 equals k1 plus k2, right? Because e to the 0 would just be 1. And then likewise, when t is 0, y is 0, we're going to have 0 equals 3k1 minus just k2. So if you solve those, I'm going to cut to the chase here. K1 ends up being 1/4 and k2 ends up being 3/4. So then my particular solution for the initial condition that they gave us is going to just follow 1/4 times the vector 1, 3 plus 3/4 times e to the negative 4t times the eigenvector 1, negative 1. And you could certainly expand that and write it in component form if you wanted to, but there's absolutely no reason to. If it's a test, I'd probably just leave the answer like that. All right, I think that's it. So we will do this a little bit in class tomorrow, do some practice, and then just kind of wrap up this unit.